Privet, and hi and welcome to my talk on Service Meshed Enterprise Java with Kubernetes and Istio, where I want to show you why enterprise developers might be interested in these cloud-native technologies, such as Kubernetes, container orchestration, and service meshes, specifically, and what that is. My name is Sebastian, written in this way, Sebastian Daschner. Born and raised in Germany, doing a lot of things with Java. I work for this company called IBM, and I'm a regular conference speaker on Java technology, typically enterprise Java and everything that involves things that enterprise projects might need. A few Java titles involved here, Java Champion and so on and so forth. And also a very interesting a fact about myself, ja lubię coffee. So that's why I'm going to show you a coffee example, right? So we have a microservice example with enterprise coffee, where I'm going to show you two applications that run in this coffee shop example. Why two applications? Well, one is boring, right? So we want to have some communication between these systems, between these microservices going on, and this is what I'm going to show you. And then, of course, we're going to deploy that to a cloud-native setting and all these buzzwords. So what I want to show you is like two applications. That is, one is called Coffee Shop, and the other one is called Barista. So if we would like to order some coffee, then we go to the coffee shop, to the user-facing application first, and then do something like order coffee. For example, by HTTP-based communication, calling an HTTP endpoint, and then inside our cluster, inside our microservice world, in this case, we will have a synchronous communication there as well, just for our example. So we have something like start the coffee brewing process from a logical term that also might be an HTTP-based communication that we call synchronously and then go back to our user. So this is one first example that I want to show you. And what we have is Java Enterprise applications, two applications. One is Coffee Shop, one is Barista. They are totally isolated and standalone. So this is the first one, built as a Maven project, in this case as a WAR, a thin deployment artifact, using Java EE APIs, and also a thing called microprofile that I will explain in a bit. And the second one is called Barista, right? So the Barista's second application looks very similar, and then we're going to have a look at them and see how we deploy that. So it's not that much about the code today, it's more about the deployment. But first, still a little bit of code for you. Just to see what's going on there. So we will have an HTTP-based communication, and in order to order a new coffee, we have an orders resource. Who of you is familiar with JAX RESTful Web Services? Okay, most of you. Who of you is familiar more with Spring REST controllers? Hands up. Okay. Looks very similar. You probably understand both. We have an URI/orders where we order some coffee, right, in a RESTful fashion. We can get some coffee. We can post some coffee orders. So we can have an HTTP GET. This is how JAX REST does it, to give us some orders in JSON, for example. And we can also order some coffee. This is this method. So then we're going to end up here if we paste some coffee order to the system. Okay. And then just quickly in the code walkthrough, what I want to show you in code as well, that we're going to have the synchronous request to the external system, to the Barista backend. So we're going to call our business logic here, order coffee. Let's step into this method. Going to have a component coffee shop, and then we do all kind of things. And also we say, brew some coffee for a Barista component. And that Barista component, that's going to be interesting later on, that is basically an HTTP client. I use JAX REST client on that side, where we're going to access that other system and then just order some coffee. So we're going to do, it's down here, an HTTP put to that other resource using an ID, and make a synchronous request, and then we return this method to our coffee shop again, and then return, of course, to the coffee order, and then the user gets a response. Okay, perfect. Now, we want to deploy this, right? Let's order some coffee. If we want to run this in a cloud-native setting, then first of all, we typically need some containerized environment. So we want to build on containers. Who of you is familiar with Docker containers? Hands up. Okay, so you've probably seen something like this, a Docker file, right? So what is that? That defines how our binary, how our instance that is running looks like, all of what our binary needs. For that Java Enterprise example, that is basically just a base image that includes our application container. I use OpenLiberty in this case, and everything that container also needs, including a Java installation, for example, or some operating system configuration. And then we add some server configuration if we want. In this case, I'll show you later. And we add our application. And that's all we need. Then we build that Docker image, and then we can go. In a Spring world, very similar. We have a base image that includes a Java installation, and then we add our fat jar and just start it with java-jar. All right, so we can build that as well. And then we could run a Docker container. You're familiar with that, for example, locally, but that's boring. We want to run it in production, right? So for that reason, we want to actually include another technology that is called container orchestration. Who of you is familiar with Kubernetes? Hands up. Okay, a few, most of them, 1/3 of you maybe. Kubernetes container orchestration, production grade. So very quickly, what is that? It orchestrates containers, like the name says. It's a container orchestration. Why? Because in a production environment, we hopefully have one little bit more than just a laptop, like a few more nodes, right? And if you want to run containers on these nodes, it's quite an effort to manage and to scale these, right? You have to go to one node, say Docker run, then you have to go to the other, Docker run, and then you have to set up some networking. Who has ever done that, right? Like Docker network, Docker IPs, it's quite an effort to do. And if you have multiple instances, you need some load distribution, load balancers and proxies and all that, quite an effort to do so. What Kubernetes does is to manage that for you. You can define a cluster of multiple nodes, and then you can just tell Kubernetes in a declarative approach as infrastructure as code, very similar to the Dockerfile idea, how the target state, how that's supposed to look like, how that should look like when you run in a production environment. That means we define something like YAML resources. Who of you has seen the YAML file format? Hands up. Who of you likes the YAML file format? Hands up. Oh, a few. OK. We're going to talk about that in a second. So we define in a declarative approach how these resources should look like in Kubernetes. So first of all, we have 2 or 3 important resource types. One is called a service, and then we have a deployment and a pod. So what is that? A service is basically a logical abstraction over an application. Right? If we have a coffee shop application and the barista one, we have one service for coffee shop and for barista. Basically a microservice abstraction on that level. And we're going to run our application in an actual runtime, in a so-called pod. So later on, that example looks a little bit like this. We have one service, coffee shop, and one service, barista. And then for each and every running instance, we have an atomic workload that is called pod. And the pod contains one or more running containers. So each pod contains one running container of our application later on. OK. Stay with me. We're going to deploy that in a second. Now, what is this deployment? A deployment is another resource type that manages pods for us. So we don't create these pods ourselves. We just tell a deployment how many instances we want to have. And that looks as follows, that we say, please deploy a pod following this schema. A pod is, again, basically a Docker image. Run this image as a pod, and in this case, run it with one replica, run one pod here. We could scale that up by defining 2 or 100 or as many as we like. That's nice. That's a declarative approach. If we want to scale up, we don't have to programmatically go to the cluster and say, install, Docker run, do this, do that. No, we tell it a declarative approach by just defining the target state. 1 replica, 2 replicas, and then the cluster will make sure that this is the case, actually. So finally, let's just deploy something. Where do I deploy to? I need a Kubernetes cluster. Who has a Kubernetes cluster? Yeah? Yeah? Can I use yours? Or, or I use one either on my laptop. There are multiple ways to install it. Or I go to a cloud offering and say, hey, it's much easier to take a managed Kubernetes cluster. That's all done for me. I use the IBM Cloud. You can get one, easy to install, done. And then you can use things like kube control, command line tool to talk to your cluster. So for example, I can say kube apply, take these YAML files and just throw it against the cluster, that desired target state, and then the cluster technology makes sure that this is the case. So let's take this coffee shop deployment folder, the whole directory, and apply it there. And then let's take the same thing for the barista application. Why? We have, well, two services. I didn't show you actually. There's the same story in the barista backend, and then we have that service as well, a service for barista and a deployment for barista. Okay, that works, and that is right now starting up. How that looks in our diagram is that then if we have this order coffee call coming into the coffee shop, we do a service lookup, I'll show you in a second, and basically end up at a running instance in our cluster. And if our instance wants to access another service, well, same story, and back, it goes through the service. Did you pay attention how my HTTP client looks, how the URL looks? That is actually a nice story we can use here. Where is my barista? Specifically that URL. Maybe you noticed I did not configure any IP address or any DNS name, you know, like test environment.barista.example corporation. No, I just said barista. That's it. And I can do that. That's a very nice feature because Kubernetes does a cluster internal DNS resolution for all the services. If I define a barista service and that service has a name, then for this name, Kubernetes will resolve while all the instances that I have. And all the pods have IP addresses on their own, and then I will end up actually at a running pod instance by just specifying barista, port 9080, which is for us Open Liberty port, whatever. Which is nice because then we don't need to reconfigure that. If you have multiple environments, you know, staging, production, test environment, whatever, you don't have to reconfigure where is my external backend or where is my database running in this environment and then change the URL. No, because it doesn't matter in which environment you're running, the name always stays the same, and then the environment does the service discovery for you. That's good for us here because here we don't care about service discovery. We just want to tell barista backend and then connect to one of the running instances. So that's a nice story about the Kubernetes setup here. All right, if we have that running in our cluster, then we can tell with the kube command line, give us the resources. Kube get services resources, for example. Now we have two services running. That's the default one, coffee shop and barista. And we also have some pods running, coffee shop and barista. Okay. And that means, hopefully, we can finally order some coffee. Yes? Good. So I can use curl, for example, as an HTTP client, as a REST client, and then I use a magic script to get my cluster IP address and say, okay, my coffee shop application, that's the one I want to connect to, runs under the context root coffee shop, and then I have resources, which I call the JAX REST application, whatever, /orders. Then we can say, please connect to that, and oh, great story, HTTP 200, okay, and we have an empty JSON array. So number of orders in the system, well, it's empty because it's based in memory, so there's no order yet. Okay, let's change that. Let's order some coffee, and if you remember, we will need to post something here. That means we have to, where is my orders resource? We have to post an object here, a coffee order, and that has a bunch of fields, specifically coffee type. And a coffee type is something like an espresso or a cappuccino, latte, whatever we want to order. In this case, okay, that means post some application JSON type here. For example, post some espresso or latte or whatever we like to have. And then good news, 201 created. Okay. And hopefully that is now in the system, and we can query for, yes, our coffee. That's good. Okay, so apparently everything works, right? I mean, it's running in production, right? And we were ordering some coffee. We asked the first system, and it called the second system. We saw in the diagram that this is the case. We saw in the code that this is the case. Well, but actually, we don't really know what's going on inside production, right? It's just a black box. we fire up some HTTP post request, and then at the other end we can ask for the coffee, but we don't know what's happening inside. So for example, we are lacking some observability and a few other concerns. And this is now where our service mesh environment technology comes into play, because this is what we want to enhance to our cluster. Oh, upgrade to Istio 1.1.2 security update. Very important. Anyway, what is this Istio? Istio is a service mesh technology. And that, like the name says, it is a mesh of interconnected microservice deployments where these deployments communicate with each other and where we want to enhance them with some things that we might need in production. For example, observability, or some more resiliency approaches, or more advanced traffic routing. So these are things we're going to have a look at. And first thing I want to show you is observability, and that's actually very, very interesting. So we have, yes, Wi-Fi went down. Let's do my magic port forwarding scripts again, and then magic, it works again. What is this? This is Grafana. Grafana is a monitoring technology that actually ships out of the box with Istio. That works with Prometheus, a time series database under the hood, and Grafana. And the good story is you don't have to configure anything to get that started. So you still look very tired. Let's order some more coffee, okay? Let's have a little bit more traffic in our system. Grab HTTP, 201 created, more coffee, more coffee. More coffee, more coffee. And then we can have a look at the observability and actually see, well, there's some traffic going into our cluster. And what you can also see, barista, the service barista. And there is also a service coffee shop. Now, again, I did not configure that. That comes out of the box with Istio, and it discovers the services that are part of the mesh and shows you some basic technical metrics here. So we can see the request volume that is coming in for that service. We see the duration of so many milliseconds and some more advanced stuff. And also what we can see that in the barista backend, we also have a traffic, so that's a good news. We actually know that there's something arriving at the barista service as well. And we see that actually, if we look closer, if you can read that the coffee shop is actually making these calls. Okay, that's interesting. So now we see that our code is actually not lying. It's really calling the barista system in this case. Okay. What also ships with Istio for observability is this cute little guy. It's a German name, Jäger. I forgot the Russian term for that, but it means hunter. And this is a distributed tracing technology where we can have a look at individual traces, individual requests that go through our system, and actually where these requests go through which actual instances. So if we try to find some traces, then we might see something going on here. This is one particular request out of the many coffee orders that I just did, and it tells us, oh, okay, we have that request coming in from Istio Ingress Gateway, that is the cluster Ingress, the Ingress traffic, going to the coffee shop application. And then, synchronously, we have another request from the coffee shop to the barista. Synchronously, because it happens in one call, they are correlated, or they actually caused here. And we see, well, this is an HTTP put to that URL. That looks familiar. That is exactly what we were calling in our client. And now we see that these two are connected. Okay, that's very interesting as well. So now we actually see that this call is calling the other system as well, synchronously. What else is quite interesting here? That is another feature that ships with Istio, Kiali, which is called the service graph technology. We can have some fancy animation here as well. So we see some requests going through the system. I know this is not that interesting because we only have, well, two systems, right? And they're just like in a straight line. But if you imagine, this shows all of your services, and this shows the actual communication and how your services are connected, which version calls which. So that only relies to what is actually going on inside your system. And if you have a more complex setup than two, then you actually can have a good overview to what is happening inside your cluster. So that's very helpful as well. All right, so how does all that magic work? I did not change anything. It's still the Java Enterprise application without any extensions. How does it work here? What happens if we deploy our workload to a service mesh environment? Instead of just applying Kubernetes, what we do, instead of having one container per pod, we're actually having 2 containers. Alongside of our main container, that is a proxy container, a so-called sidecar container. For each and every pod, if we have 3 instances, then each of these 3 has its own proxy container. And what happens if we have some communication into the service, then this actually ends up at the proxy container, and then the proxy container will or might forward to our main application, to our main container as well. And if our main container, if our application calls another external backend, that also goes through the proxy to the other proxy of that other instance, and the same way back. So we have all that communication injected and happening through these proxies. How that works internally is with IP tables and Linux black magic, so we don't have to configure that. That is done by Istio. Our application still just accesses Barista. All right. So if you're familiar with Spring proxies or Java Enterprise proxies, this is very much a similar idea, right? Because now these proxies have the full control and see everything communication-wise, what's happening inside the cluster. So that means if we have some requests going in, this proxy sees that request, can log it, and emit that information out of band for our monitoring to work later on. And in the same way, this proxy could manipulate that request if it wants to and send it somewhere else. So later on, we could have another component, and that's also part of Istio, so-called control plane, that communicates with all of these proxies individually and configures them and gets some information out of them to get all this information here. So then we have the idea, okay, how does this monitoring work here, or how does the service graph work? Well, because we see all the requests happening. Okay, one question left. How does the distributed tracing work? Because, if you think about it, just because if we have a request going through that system, this arrow, and just because we have a request here, we don't know that this request is actually correlated to the other request, that they belong together, that one caused the other. Just because they happen to happen at the same time, well, we don't know. So this is the only thing where we have to do something, actually, because what happens or what needs to happen, we have to pass some correlation IDs, some identifier that we know that this request is correlated to the other one, right? How that typically works, depending on the communication protocol, is using some HTTP headers. There is a de facto standard with open tracing and open zipkin that is where we have headers called like x-b3-span ID, that is trace ID, maybe you've seen them. And we need to, pass these headers. So that's actually quite an effort, because what that means, if we go to our resource, that is our JAX-REST resource, where we have an incoming request, right? And that request, that HTTP request, has these trace and span IDs already. They are generated by the proxy initially. Okay, that's good. But now we need to pass them up until the client to know that this is actually a single synchronous request, right? We need to keep that information in the current context. So actually, we would need to go here, take the HTTP request, say request get header for xb3 span ID, xb3 Istio distributed tracing. There is actually some documentation here how that can be done using JAX-RS. Something like this. Take a lot of HTTP headers. Looks ugly, right? Because now you can imagine what you need to do. Well, you need to take them here, either store them in a span context in an object, where you have them at the thread local or somewhere locally in your request thread, or you pass them immediately as a parameter here. You pass them as a parameter here. You pass them as a parameter here. Then you extract them and put them to the HTTP request. This is ugly, right? A lot of boilerplate code. Well, luckily, we don't have to do that. because in this case we're using Java Enterprise, where we can have an extension called microprofile or microprofile open tracing that actually supports this. So I added this in the code here, a dependency, but actually in your code you don't even have to have that dependency, because, well, what we only need to tell is our runtime, our implementation, I use OpenLiberty, to take all of these headers to use that functionality. And what we have, oops, this is now a server configuration for Liberty, but doesn't matter, where we tell our server or our container the features that it should use. So I want to use Java Enterprise, whatever, and microprofile as well, because of microprofile open tracing. And that's Liberty specific, but there is an integration for that, for open tracing, where we can actually pass these headers. Or in other words, where we don't have to do anything. If we add this, then the JAX-RS implementation, if we have an incoming request that has all of these headers, we'll actually take these headers and store it in a current context object. And if in the same synchronous request execution path, we have an HTTP client, like, where is my class? Like here, then it will take the current object, including this information, and attach it again. And that's done. And that's good for us. And that's the reason why that actually works, why we have a trace where this information is passed with the correlation ID. OK, so that means this is the only thing we have to do. Actually, we don't have to do anything, luckily, but we have to tell our runtime to use such a feature, and that's it. Same is implemented for Spring. Same integration where that is done using HTTP-based communication, so that we don't have to pass this information. OK, that's good. Anyway, that's about it for observability. There are a few other things, that we want to be interested in. For example, we can have some further traffic management and some further resiliency approaches. I want to show you both. Because since we have the proxies have the full control over everything that is happening, all the communication. Because the proxies see all of the HTTP requests, and these proxies, internally, they're actually Envoy proxies, C++ technology for proxy technology, and they are layer 7 aware. They know the HTTP protocol, so they can read information and then just manipulate the routing, for example. So what we can do is saying for this proxy, hey, if you get that request to that system, don't send it to the system, send it actually somewhere else. There might be cases where that is interesting. So what we can do in this case, we can implement some more behavior. Let's start with resiliency. What happens if, I define some timeouts here. Maybe you attended the session yesterday about bulletproof applications, or timeouts, for example, is always a good idea. But what if our application here does not handle resiliency properly, right? What if it doesn't define timeouts, or a few other things like bulkheads on a connection level? Since we have our proxies here, the proxies can handle these. So for example, the proxy can implement some timeout behavior here, even if our application doesn't do that. Let's do that, just for fun. In order to show you this, I'll briefly introduce that concept, how we configure Istio. More YAML, yay. So this is how we configure Istio. If you're familiar with Kubernetes YAML files, you will notice they look very similar. What is that? This is, in this case, an Istio resource type, not a Kubernetes one, and it says virtual service, right? We see that this comes from the Istio extension. So the good news is the look and feel, the developer experience is very much the same. We can use these Istio types in the same way like we would use Kubernetes types. Right. So you see they look very similar. We also have a specification here. And we can also use the command line, the kube control command line, to manipulate these types. So for example, we can say kube control get services, right? That's normal. But also with Istio, we can say kube control give me the virtual services. In a standard Kubernetes cluster, this would not work, right? But since my cluster is enabled with Istio, this is the extension that works then we can use the same look and feel. It extends these types. How does it work? Kubernetes has an extension API where we can define our new types, right? So we can define a virtual service, we can define a smartphone or a water bottle, and have our own types if we like to. That's good for the developers because, same look and feel. All right. Now to the types that we're using here, actually. This is called a virtual service. And the virtual service defines some advanced traffic routing for, well, a service that is part of the mesh. Per default, all of the Kubernetes services are part of the mesh, coffee shop, barista, but we can also have some further entries for the mesh, or have something like wildcard services. So this is why they're called virtual services. We can do a little bit more things than compared to just plain Kubernetes. But what this does, this is the default routing that is best practice to define. Very boring. It just says everything that would you route to a barista service, route it to the barista service. Okay, great. Subset version v1. So what we can do already, we can define subsets. We can take our coffee shop or our barista service and further split it up into multiple subsets. We're going to see why we might do that. And we have another type that is called destination rule that defines some further policies of a service, of a destination that's being called. For example, which service is even allowed to call my service, and so on and so forth. And it also defines the subsets here that we have for this version, v1, that's the only one. And that subset is actually using Kubernetes labels. So these labels on the pod that just tell us some meta information. Okay. Now the other routing part for the coffee shop application is a little bit bigger. That also includes a so-called gateway. A gateway is very similar to Kubernetes ingress. That is the cluster incoming traffic into our cluster. So we have HTTP 80, okay, comes into the cluster, and then we route it to the coffee shop, port 9080, and that's it. Also very similar. That is basically this setup. We have a route here, and then a route, well, to the barista service. That's it. Okay, this is boring because that's just a default example. But what if we want to, let's close all these resources. But what if now we want to add some resiliency, for example? So we say, what happens if we don't have a timeout behavior, a proper one? So like here, we want to add some timeout behavior if that application doesn't handle it properly. So we might want to enhance our coffee shop service, our coffee shop virtual service in this case, with that timeout behavior where we simply can annotate that route with a notation timeout. Timeout of 1 second, for example. So who of you likes YAML again? Because this is what I dislike a little bit about YAML. You never know whether this is correct. Oh, this is correct? Did you see the difference? Or maybe this is correct? No, trust me, this is correct. We're going to notice in a second. So luckily we have a proper verification, but the structure is might be a little bit confusing. So somebody once recommended you have to take a ruler and place it to your screen to see, oh yeah, this is correct. Okay, continue. Now we have these requests going on. Coffee shop. So if we now update this is coffee shop deployment routing. And we say, okay, this virtual service is now updated and we have this timeout behavior. Okay, works, right? Well, yes, I guess. Well, we don't know. It's less than 1 second, so we don't know whether it works. How can we test that timeout behavior? If you have attended yesterday's session, then you might already know, well, actually, we can now either take that application and swap it out to something else. For example, a mock server for our test environment, right? We want to define a test harness situation where we say, now test the timeout behavior of my setup, right? Always test stuff. If you attended yesterday, always test your resiliency. Now, how we can test that? Well, multiple ways. We can, for example, swap out this application for a mock that says, oh, delay, 200 milliseconds or 1.2 seconds. So you test the behavior. Or even better, since we are in that service mesh environment where our proxy can literally do anything with our communication, then just for fun, the proxy can mess things up for testing reasons. So what we can say, hey, this barista backend should actually be a little bit faulty. For example, we can define some faulty behavior. Fault. For example, we can add a delay. We can just say, by the way, make the things slower so that in the first place we will trigger the timeout and we will see if the timeout reacts properly, right? So we can have something like a fixed delay of 2 seconds or 3 seconds, but not all the time, but only in 50% of the cases. Okay, ready for production, right? Perfect. Let's add this code, barista deployment routing, and then we update our virtual service. Please do not run this in production. And then what happens? Well, either we immediately get a response of 201 created, or it takes, 1 second until the timeout fires, but not longer, not 3 seconds at least. So in this case, that tests the timeout behavior. In the same way, what we could do is we could throw some faulty HTTP responses. We can also test the behavior of our application in this case, right? So we can say, okay, what if we throw a 500 server error, and what does our application do with it, right? So very nice way to test resiliency in this case, since we have the full control without changing our application. We literally can go to a test environment that we deploy in the very same way with the same applications, no changes, no mock server, same story, but then just use the service mesh annotations, this extra behavior to drive our test scenarios. Okay, let's please dial this back. And hopefully that works again. So that's one thing we can do. We can add some further resiliency if our application doesn't handle it already. What we can also do, which is actually very interesting, especially for more advanced scenarios, is some traffic routing, for example, for deployment scenarios. So if we want to do things like canary releases or A/B testing, where we have multiple versions of the coffee shop application at the same time being active, so not a typical deployment of saying, take version 1, shut it down, take version 2 in a zero downtime approach. Kubernetes can already do that. But I mean where we say deploy version 1 and also deploy version 2 and let them running for a while and then test which version is better. A/B testing, route specific users to this and to this version and see how they react. Or gradually roll out a version by do some canary releases by rolling out 5% or 1% first and then gradually increase that number. So we can do that using Istio. Let's do some more YAML live coding. That's exciting, right? Let's remove this timeout as well. So what we have this destination. So if we had another version, we simply could change that destination. But in this case, what I want to do, let's do the canary release first. We can say we have a weight of, let's say, 30% of the new version and a weight of maybe 70% to the old version, where we have multiple destinations. By the way, in YAML, this is an array. The dash, it notifies array instead of object. Yeah, I know. So 2 destinations here, multiple destinations with a weight, so 30%, 70% in this case, or 5%, 95%, with a new version. And also what we need, we need 2 subsets now, version v1 and v2, right? And in this case, we also need a deployment. I actually already have one if you paid attention, because now we need a new version that backs the same service. So it's the same service, coffee shop, but it has a subset. How do we define these subsets? With another Kubernetes label. Per default, or as a best practice, they're called version or whatever we want to call them. It doesn't have to be v1, v2, can be any name. So that deploys a different image here, and then we can simply, deploy them both. That is actually already the case if you paid attention, we have two pods, coffee shop and coffee shop v2, and then we can route to them both. So let's apply this. Control, coffee shop, deployment, routing. And then that hopefully works. And then what we have in this case, let's stop there for a second. Curl, let's ask for the orders in our system. So sometimes we get one request. Let me length. Oops, if I know how to spell. So now sometimes we get a request with that many responses, and sometimes, so that's an array that contains 1,600 coffee orders, all the coffee that we just ordered, or we have our new system, version 2, that we didn't use until now, where I only have one order in the system, right? So that's either this response or this response, right? Depending on the number of coffee orders in the system. So then we see that, well, true, that we have different resources, different responses. That's about A/B testing. So we can change that behavior here by just proxy routing. Kubernetes, same service, coffee shop. What else can be done is, sorry, that's canary releases. What else can be done is A/B testing or some scenarios where we more specifically want to define to which version to route to. So not just random, like 70%, 30, but based on specific criteria. If, for example, you have a specific user group that you want to test, where you want to attach more information, or high-risk customers that you want to treat differently, or whichever criteria you want to have. Now we can use, let's dial this back, we can use all the information that we get using our HTTP request, everything that we could read out, for example, HTTP headers, to make our decision where to route that stuff to. So for example, we can say we have this route, version 1, default version here, and besides that we also have another one, now it's getting interesting, with YAML, where we match. So that is a different HTTP route with a match where we say, for example, for HTTP headers, take a header such as your browser, the user agent, or any other header, high-risk user, true or false, whatever you want to have, and then say, do this with, it's the default Istio example, with a regex of Firefox browser, for example, whatever criteria you define, and then you define, okay, this criteria should actually go to this destination, version 2. And this will take precedence over this one. If that doesn't match, then the other route is being taken. So you either go to that or you go to that. Let's apply this. I hope my YAML live coding works. So now if we say that again, we always get the same response back. Oh, somebody is ordering coffee. Or what we get if we say user agent Firefox, then we get always that response. So always the same based on some criteria, whatever we would like to have. Okay, that's another scenario. So more advanced traffic routing. So what else? What else is there? If we would like to apply that, this is just the mechanics that we would do. But of course, we don't go and edit YAML ourselves. Please don't do that. What we would like to do is we want to define a proper approach how to let our continuous delivery pipeline do that. So ideally, we have that approach using some automation and using some more advanced features with integration of observability, for example, to define a proper deployment scenario. For example, saying, using this service mesh technology, if you want to deploy a new version of, let's say, coffee shop, or actually can be any service version of your mesh, then use that approach of don't do a big bang deployment, do a canary release deployment with 5% or 1% of the traffic first, then have the integration into our monitoring here and see whether the whole thing immediately blows up or not. And if, then roll it back. If not, you can roll out further, 5%, 10%, 25%, whatever you would like to have, in an automated approach. So this is what you should define. Don't do that, what I just did, in production. Don't edit YAML files. You will fail, I promise you. But then this works, better. Also, what we can see here, let's order some coffee. Again, that was interesting. Post, order coffee. We see that our service graph technology, what I promised you before, can actually show us a little bit more information. Once it has the information, that we have some incoming traffic as well, where which version we use in this case. So this Kiali, that's a nice side information as well. It actually knows about the Istio config. It's Istio aware, and it knows the things like subsets. So we have, which version is being used currently with that traffic, and which version fails. What we've seen with the timeouts before, it would show you as well. So you have some more information of if you do some of these canary deployments right now as well. That gives you a nice idea. What else I want to show you is a more automated approach. So instead of what I just did before, let's have some approach. I have some deployment script for that. So let's delete everything in that deployment directory again here, because then I can deploy a new version. Let me just show something here. We use a curl on that side, and then we say kube control, given the pods continuously. So we have one pod because the other one is right now terminating, and let's deploy one version of this. So now we use a templating approach where we actually generate everything that I just did. Use version 1, then add the subset version 2, now 5% routing, now 10% routing. Everything that I did manually, we want to have a proper approach here. So in this case, what I can have is curl, give me the orders. Oops, yeah, that's currently empty. Let's ask without status, and now we need to wait until that new thing is up and running. That is, by the way, what we now can see that we're running in this Istio environment. We have 2 containers inside each and every pod, right? If you're interested in that, I can show you how we see what is actually done by Istio. That's a very nice story. Kube control describe pod coffee shop. I told you we have multiple containers here in this pod, right? But if you look into the YAML that we defined, there's only one, right? Containers, 1 container here. Not 2. Where does the second container come from? Well, that is being injected by Istio. There is a component called sidecar injector, and you can guess what that does. Well, it injects the sidecar. So that means we don't only have our coffee shop here in our pod, we also have a second container that is called, where is it? Istio proxy. So that is the Envoy proxy actually that runs here. And this uses, Envoy under the hood, and this is the reason why this pod has actually 2 containers, just as a side note. All right, so we have this. Okay, somebody is hitting my application. So somebody in the audience, that is interesting. Anyway, it doesn't matter, you can continue. I don't care. And what we can do, we can, again, ask the length here. It just changes the length, but it doesn't matter. And now we have our version here. And if somebody hits it, please stop for a second, because otherwise we will be confused. It still works, but then we count in a wrong way. So now what we can deploy here, take the old version v1, deploy the new version v2, using that new image here. And what we do, well, in this case actually, we can say wait for the deployment. Now you see there is a new deployment happening. So first of all, that's a zero downtime approach. That means, well, our application is not being changed. We still have version v1 backed by the deployment v1. And it still runs. That's good. But we define how that's supposed to be deployed in that automated approach. So first of all, we say, take the new version and deploy it. OK, now we wait until the new version is being deployed. And then if that is the case, that is all handled by the script, by the automation, then it says, OK, now it's there. Now route 5% of the traffic to the new version, which in our case should yield the response, I hope it's 0, until unless that person continued to fire it, and now it's also 2. Oh, no, is it 1? No. Maybe it's also 2 in the other. No, it's 0. OK. Well, it's random. We can actually speed it up a little bit. And then you see how gradually the responses of the new version increases until that is being fully rolled out with 100%. So what happens under the hood, we can also show that, is that kube-control get virtual services. Just for fun, we can do that again to see this. Okay, let's do some magic here. Virtual services. Given the virtual service of the coffee shop and output that as YAML. So we see the response here and do that continuously just because we can. And now we, oh God, where's my cursor? There it is. We roll back from version 2 to version 1. So same story back, and then we will see that once that is being deployed, we now deploy the old version, that this gradually changes the routing. So what this is, it shows the live state of my virtual service, of my Istio resource, and shows you what's happening under the hood. So let's open up another one. Let's wait for the pod until that is up and running, and then hopefully we get some response here. And then you see the same thing, how that changes. In general, again, what you want to define is a proper automated approach that is integrated into your deployment pipeline, so where you don't have to do that, right? And service meshes is one way how you can define that. Whatever technology you're using, this should be your goal here. So now actually both are 0, so you don't see a difference in the response. But now you see how that weight, oops, let's make this smaller so you'd actually see it, how it changes from 5%, 25%, 75%, how we're gradually rolling that out. So that is that change that's done here. I hope that shows you a little bit what we can do using the service mesh, in this case using the advanced traffic routing. Very nice for us. We don't have a change in the application, on the application level. We don't even have to have a change on the Kubernetes resources. That's done using this routing. And we can also do the routing inside the traffic. So that's not only done on a gateway or like Kubernetes ingress or OpenShift route level, also cluster internally. We could do the same thing for the barista service and then routes to multiple subsets. And you can also have different subsets of different versions that are deployed to the cluster. But don't do it, don't overdo it too much, otherwise it becomes like super confusing. So I hope that shows a little bit of that is working. And again, nice story. We see now that is still using both in this case. Only uses the GET request of our service graph. Same story here that we see in the monitoring. Go to the coffee shop service. So we hit the request and how they're being used inside all these observability information. All right. So a few key takeaways for container orchestration already. What we saw, if we using plain container orchestration, Kubernetes only already, is, well, Kubernetes gives us some service discovery capability, which is one of the biggest killer feature. We don't have to do that ourselves. Is that possible using homegrown technology? Yes, of course. Everything I showed you is possible, was possible 20 years ago, 30 years ago. And hopefully enterprises have done that already. But from my experience as a consultant, they didn't. Or in other words, if you do it in a homegrown approach, you always have to implement all of that yourself, right? And if you use a technology or a de facto technology, then you can actually, rely on these frameworks doing that job for you and being shipped with these approaches out of the box, such as, rolling update deployments. Kubernetes can deal with zero downtime approaches, has controllers being built in, point deployment and scalability. What happens if, well, you kill a pod or the pod crashes? Then out of the box, a new pod will be created, thanks to the deployment controller. So that's a nice story about that. It's being built in with that already out of the box. Another thing we can do, well, the whole networking and configuration. It's quite an effort with IP tables and all that routing that is being used for containers to manage such a cluster of containers ourselves. If you've ever done that, yeah, good luck. It's fun. But Kubernetes does that for us. Now for service meshes, technologies, a few key takeaways. Service meshes in general transparently add some concerns that we might need in production to our microservice deployments, to our applications, without changing our applications, right? So that's the nice story. It's actually very similar to the deployment and development model of Java Enterprise or Spring. If we have, somebody said AOP for applications, aspect-oriented programming, what we have in Java Enterprise, if we have a simple class, and just because we annotate it with add path or with stateless, then we add a lot of these concerns that we otherwise need to implement ourselves, right? Like HTTP request handling, transactions, database communication. All of that is already being handled, in this case by our application server, by these aspects. And we only define our business logic, our code. And here is quite similar. We define these aspects in a transparent way without changing what is actually running, without shipping our implementations with that, and it's being implemented by the environment. Aspects such as what we saw, routing, load balancing, resiliency concepts, a few as a backup, telemetry data or observability in general. Authentication, authorization, that's another nice story. We can actually have some mutual encryption between these services with certificates that are actually provided by the service mesh environment by Istio. So Istio can inject some certificates into the proxies, and then the proxies will mutually encrypt our communication without our application needing to change anything. So we still use the plain HTTP communication, which is good for us because it's easier, and good for the proxy, so the proxy can actually see the information of the HTTP request and then use that information and encrypt it over the wire. That's very nice. What I also very much like is how it integrates well with the Java Enterprise approach. So just what I said before, it's a question of responsibility. That's typically how Spring Boot came from that history. Spring Boot supports all of that and much more by shipping it in the implementation already. So you can do that as well. Then you don't necessarily need a service mesh environment. But the question is, especially if you have a lot of microservices, a lot of deployments, each and every implementation would need to ship all of that functionality individually, right? And you would need to add it into your deployment artifact. So the question is just where you want to put that responsibility in. If it's actually a responsibility of your application to do things like service discovery. And I believe, well, actually not. Because in my code, like in the HTTP client, I simply want to say, take that barista backend. How you do it, that's configured somewhere else, in the environment, for example. Same story was the case for application containers, right? How do we handle our database connections? How do we handle HTTP or transactions? Well, we don't care as enterprise developers, or we don't care that much. We might declaratively specify, add transactional, how that is being done, but implemented, well, that's being done by somebody else, the implementation. So in this case, we actually specify proper responsibility layers in this case, and we can focus on, well, business logic, for example. And this is, well, that's my story of where we put the responsibility in. And from a Java programmer's perspective, then we can actually, using this technology, focus on more what we should focus on, that is implementing business logic. I hope that was helpful. Spasiba. Thank you very much.